What effect does potassium chloride have on catalase? By Will Bailey.
Abby Casey,
Rachel Antuna,
and Madeline Murillo. Based off of prior research, peroxidase/catalase speeds up the decomposition of hydrogen peroxide to water and oxygen.
The enzyme catalase is important because it serves to protect our cells by counterreacting and balancing the continual production of hydrogen peroxide, which is a byproduct of cell metabolism. This is important because catalase is a powerful antioxidant support. In conclusion, catalase creates a speedy reaction against hydrogen peroxide-free radicals.
Based on the chart that was taken from the Dong article, the treatment of potassium showed to have little effect on the overall enzyme activity. This means by adding potassium chloride to the assay will not have a significant impact on catalase activity.
The study question was, what effect does potassium chloride have on the enzyme catalase? And the hypothesis was, an increase in the concentration of potassium chloride will cause the rate of enzyme activity to decrease.
The positive control was tested by adding 4.85 milliliters of 0.02 molar potassium phosphate buffer, 0.50 microliters of glycol, and 50 microliters of turnip extract. The turnip extract was used because it contains catalase. Then right before the cuvette was placed in the spectrometer, 50 microliters of hydrogen peroxide was added. This was done last because as soon as the hydrogen peroxide is added to the solution, the reaction immediately starts and the solution starts to turn brown. The goal of the positive control was to reach an absorbance of 1 around 1 minute, but the positive control ended up reaching an absorbance of 1 after 120 seconds.
After the positive control was tested, the same process was repeated with the addition of potassium chloride. Once again, the potassium chloride was added before the hydrogen peroxide. 3 different molarities of potassium chloride were tested: 0.001 molar, 0.005 molar, and 0.01 molar. Each molarity was tested 3 times to ensure better results. The absorbance of the final solution with all the components was recorded every 20 seconds over a period of 2 minutes.
The absorbance was measured by using a spectrometer with wavelengths being set to 480 nanometers. The absorbance of the final solution with all of the components was recorded every 20 seconds over a period of 2 minutes.
This graph displays the absorbance versus time. The overall trend of the graph was as time increased, the absorbance increased. This trend was observed because as the reaction proceeded over time, the solution would become darker and darker in color. From the results, it was shown that the positive control took well over a minute to reach an absorbance of 1, which means the reaction proceeded at a slower rate than expected. This is not a big deal because the positive control data was used in comparison to the data from the other 3 treatments. There was no significant difference in the absorbance of all treatments in positive control between time 0 seconds and 100 seconds. In the last 20 seconds, there was a visible difference between all of the treatments and positive control.
This bar graph compares the absorbance of the positive control in all 3 treatments at time 60 seconds. Error bars were added to show the significance between the positive control and all of the treatments in this experiment. From the 95% confidence interval, it was seen that the positive control error bar overlaps with the first 2 treatments, 0.001 molar potassium chloride and 0.005 molar potassium chloride. This means that there is no significant difference in these 3 sets of values. On the other hand, the error bar corresponding to 0.010 molar potassium chloride and the error bar on the control did not overlap. This means that there is a significance in these 2 sets of values. Next, a t-test was analyzed by comparing all 3 treatments to the positive control. When comparing treatment 1, 0.001 molar potassium chloride, to the positive control group, the p-value was 0.94. With a p-value greater than 0.05, it can be concluded that there is no significant difference between the positive control and treatment 1. Further concluding that the addition of 0.001 molar potassium chloride had no effect on the enzyme catalase and the reaction as a whole.
This exact same scenario was seen in treatment 2 as the p-value was 0.099, which is greater than 0.05. However, the p-value in treatment 3 was 0.018, which is less than 0.05. This means that there was a significant difference between the control treatment and treatment 3, which was the addition of 0.010 molar potassium chloride.
Prior to the experiment, we hypothesized that an increase in concentration of KCl would cause the rate of enzyme activity to decrease. However, the results show little change in enzyme activity as time increased, which was also seen in the Dong article.
From the Dong article, it was concluded that the independent variable potassium would have little effect on enzyme activity. Also from the article, it was concluded that other metal ions do play an important role in the activity of enzymes. For example, chromium significantly impacts enzyme activity. If this experiment was performed again, it could be improved by making a more precise reading of the absorbance of the control group. Also, preparing the potassium chloride solution at a higher molarity could yield a more significant impact on enzyme activity.